Welcome back to An Introduction to Oceanography from the Cengage Learning Textbook Essentials of Oceanography, written by Tom Garrison and Robert Ellis. This is the 8th edition, and now we're taking a look at ocean circulations. In the last lecture, we looked at atmospheric circulation. What makes the wind blow, and what impact does the blowing wind have on the ocean? Now we're going to take a closer look at the ocean and how it moves, not just those surface currents that we may be familiar with, but what's happening deep down in the ocean. We'll start out with our main concepts. All right, our first concept, ocean circulation is driven by wind and the differences in water density. Second, we'll look at the fact that surface currents are wind-driven movements of waters, but also driven by density differences between temperature and salinity. We'll talk about what a gyre is and how the Coriolis effect creates those gyres, large surface currents that move in circular patterns on the ocean surface. We're going to get into the El Nino and the Southern Oscillation and why they are exceptions to the normal wind and current flow. We'll talk about water masses that form at the ocean surface and how they retain their distinct properties as they sink and sort into identifiable layers. So first and foremost, ocean currents are driven by winds. The westerlies and the trade winds are two of the winds that drive the ocean's surface currents. And you can see the westerly is going to blow from west to east at the surface, and the trade winds from east to west. And what that allows to happen is that you start to get a clockwise flow in the northern hemisphere and then a counterclockwise flow in the southern hemisphere. What that ends up actually looking like are these large, what are known as gyres, which are actually going to be the currents of the ocean turning in a clockwise flow in the northern hemisphere and then a counterclockwise flow down here in the southern hemisphere. And each of the main ocean basins has one of these large gyres, one of these circular flows. So about 10% of the water in the world ocean is involved in surface currents. Only that 10%. Water flowing horizontally in the uppermost 400 meters of the ocean, driven mainly by wind friction. So winds driven by uneven solar heating. Again, remember, at the equator we heat up, at the poles we cool off. So air rises at the equator, moves north and sinks at the poles and moves back south. So winds are driven by uneven solar heating of the Earth's surface. They spin due to the Coriolis effect and drive the movement of the ocean surface currents. The prime movers are the powerful westerlies and the persistent easterlies, those northeast and southeast trade winds. Surface currents travel at a speed no greater than about 3% of the wind speed. So if you have winds moving at 100 miles per hour over the ocean, the surface currents only move there at about 3 miles per hour. So the wind really has to be lots and lots of wind to create these surface currents, lots of persistent wind. So what are the effects of those ocean currents? They transfer heat from the tropics to the polar regions, they influence weather and climate, and they also distribute nutrients and scatter organisms around the globe. So a combination of 4 forces, the sun's heat, surface winds, Coriolis, and gravity, circulates the ocean surfaces clockwise in the northern hemisphere and counterclockwise in the southern hemisphere, forming the gyres that we just talked about. So in this illustration, well, for those are the 2 gyres that I showed you in the last slide. In this illustration, the North Atlantic gyre is a series of 4 interconnecting currents with different flow characteristics and temperatures. You have the North Equatorial Current, you have the Gulf Stream, the North Atlantic Current, and the Canary Current. And these currents are driven by the northeast trade winds and the westerlies, and they result in this one large gyre in the North Atlantic. So in the northern hemisphere, the topmost layer of the ocean will flow at about 45 degrees to the right of the wind direction. So it's the same in the southern hemisphere, but it's to the left of the wind direction. So let's just talk about the northern hemisphere, where Coriolis will deflect the ocean current about 45 degrees to the right of the wind direction. Surface water blown by the winds at point A will then veer to the right of the initial path and continue eastward. And then water at point B veers to the right, here's B, and continues westward. And again, creating that ocean gyre that we see in the major ocean basins. And this veering of 45 degrees is known as Ekman currents, or the Ekman model, or the Ekman spiral, depending on how you want to define it. So again, the wind at the surface is blowing in this direction, And because of Coriolis, the surface water blows at about 45 degrees to the right of it. But each additional layer deeper and deeper in the water also blows to the right, or moves to the right of the layer above it. So as you go deeper and deeper, those ocean currents continue to move to the right of the initial flow until you get to the very, very bottom layer, which almost is moving in the opposite direction. So a body of water can be thought of as a set of layers. The top layer is driven forward by the wind, and each layer below is moved by friction. Each succeeding layer then moves with a slower speed and at an angle to the layer immediately above it, to the right in the northern hemisphere, to the left in the southern hemisphere, until water motion becomes almost negligible. Although the direction of movement varies with each layer in the stack, the theoretical net flow of the water in the northern hemisphere is about 90 degrees to the right of the prevailing wind. Now, the previous slide we talked about 45 degrees. That is going to be for the surface water. When you consider all of the water movement in the entire deep layer in which the movement is affected, the net effect is about a 90 degrees. So at the surface, it's about a 45 degree flow, but the net effect is about a 90 degree flow to the actual wind motion. And again, this is known as the Ekman spiral. The effect of Ekman spiraling and the Coriolis effect cause the water within the gyre to move essentially in a circular pattern. This is the northeast trade wind. This is the water at point B. The direction of movement is about 45 degrees, and then it continues to be deflected to the right, and the water continues clockwise. It does not continue clockwise into a spiral, but instead generally moves in that circular motion around the basin. The movement of water away from point B is influenced by the rightward tendency of the Coriolis effect and the gravity-powered movement of water down the pressure gradient. That gravity-powered movement of water down the pressure gradient occurs because this Ekman spiraling causes water to pile up in the center of the gyre, and so water wants to flow down that pile, downhill off that pile. There is a hill of water in each ocean basin. There's a hill of water in the North Atlantic formed by the Ekman transport. The surface of the North Atlantic is raised through wind motion and Ekman transport to form a low hill. So water turns clockwise and inward from the dome, then descends under the dome, depressing the thermocline. So you can see it depresses down that thermocline. Water movement from B turns westward and flows along the side of the hill. The westward moving water is balanced between the Coriolis effect, which would turn the water to the right, and the flow down the pressure gradient, which would want to cause it to go to the south, which is driven by gravity. Thus, the water in a gyre kind of moves around the edge of the ocean basin. So it's a combination of the Ekman current turning it to the right, combined with this downhill movement turning it south, that just causes it to generally and gradually move in a clockwise flow around the ocean basin. So another way to look at this surface current flowing around the periphery of the ocean basin, again, the water at point B is being blown from the north and east by the trade winds. That's want to deflect it to the right by the Coriolis effect. Continued deflection by the Coriolis effect would theoretically then cause that water to spiral in if there were no other impacts on the water. But the other impact on the water is the fact that that inward turning, that right turning, causes the water in the middle of the ocean to pile up. It's a small hill, but it's there nonetheless. And there is a gradient, or a pressure gradient, or a force down that hill. So that is this arrow from north to south. The arrow from south to north is the Coriolis effect, and the net effect of the water is to be deflected to the west and then basically around that ocean basin. Now, because the Coriolis effect is stronger to the north than it is to the south, that hill is also offset to the west. And this is what that looks like in terms of the hill being offset to the west. Without the Coriolis being stronger to the north than it is to the south, you'd have this nice round circle around the ocean basin. But because Coriolis increases from the equator to the North Pole, the Coriolis effect is going to be stronger in the North Atlantic. Because it's stronger in the North Atlantic, the water is deflected in a greater force to the right in the North Atlantic, causing this quicker turn. So your North Atlantic flow is a much broader flow. It is much wider across the eastern side of the Atlantic basin, whereas here, there's less of a turn to the north, and the water gets sort of piled up along the edge of the basin. The effect of this broader flow around the east side and a narrower flow around the west side, the water flowing in a broader channel essentially will move more slowly. The water flowing in a narrower channel will move more quickly, and this is known as western intensification. Without the Coriolis effect, the gyres will look like this. With the Coriolis effect, and the fact that the Coriolis effect is strongest in the North Atlantic, it makes a stronger turn to the right, and it turns more quickly than at the equatorial Atlantic. So what ends up happening is you get this western intensification. An equal amount of water flows all the way around the gyre, so the water has to move more quickly on the west side in this narrower channel than in the broader channel on the east side, and that is known as westward intensification. And again, here's another look, a cross-section of the flow of the North Atlantic, known as the geostrophic flow, which is the modeled flow. The Gulf Stream is a western boundary current. So the Gulf Stream is on the west side of our mound, on the west side of the basin. It is a western boundary current. It's on the west side of the basin. It's narrow and it's deep, and it carries warm water very rapidly to the north. The Canary Current is on the east side of the basin, and the east side of the slope. It is a broader water slope, so it's much shallower. It's an eastern boundary current, a shallower current, a wider current that carries cold water at a much more leisurely pace to the south. Although this gradually sloping hill is only about 6.5 feet high, it really wouldn't be apparent to anyone traveling from coast to coast. It is large enough to help steer the gyres in each basin, in this case, the North Atlantic gyre. So what does this look like, the surface currents around the ocean basin? Two things are going to happen due to western intensification. You're going to get warm water flowing up the west side of a basin and cool water flowing down the east side of the basin in the northern hemisphere. That's one thing that's going to happen. And really three things. The second thing is going to be the western boundary current is going to be narrow and stronger. The eastern boundary current is going to be weaker. And that hill we talked about in the center of the Atlantic Ocean is offset to the west. The actual hill is going to be offset to the west. If we look back here, the hill is offset away closer to the western boundary current. And we see that here as well, with the center of the geostrophic hill being offset to the west. So the average height of the surface of the North Atlantic is shown in color in this image from the Topaz Poseidon satellite. Red indicates the highest surface, green and blue the lowest. So you can see that this hill is offset to the west with the western boundary current, the western intensification. And really, this hill is only about 2 meters or about 6.5 feet above the surface. So you really wouldn't notice it if you're traveling across the Atlantic Ocean, but it's enough of a hill to cause that gyre to go very much around the Atlantic Ocean in a circle. All right, there are 6 great gyres. There is the North Atlantic gyre, which we talked a lot about, the South Atlantic gyre, North Pacific, South Pacific, and then the Indian Ocean gyre. And you can see how the west side of the northern hemisphere carries warm water north, because what we're looking at here are sea surface temperatures. Here's the North Atlantic, the Canary Current bringing cool water south. In the Pacific Ocean, you've got the Kuroshio Current carrying warm water north, and then the California Current carrying cold water south. Here you have, in the southern hemisphere, it's the opposite, where warm water is traveling toward the poles here, and cool water is traveling toward the equator here. Same thing in the South Atlantic. Warm water is moving south, cool water is moving north. And then in the Indian Ocean, you have that warm water moving south and cool water moving to the north. So this is an illustration of sea surface temperatures, not the heights like the previous slide, but temperatures, showing the general direction and pattern of the surface current flow. The purple color around Antarctica and west of Greenland indicates water below 0 Celsius, the freezing point of fresh water. Note that the distortion of the temperature patterns that we would expect from the effects of solar heating alone, that is just warm at the equator, that warm water is twisted northward in the northern hemisphere and counterclockwise and southward in the southern hemisphere. All right, so this is what those 6 great currents look like, and of course the arrows indicate the temperature of the water. The Kuroshio carrying warm water north, the California Current carrying cool water south, Gulf Stream warm water north, and the North Atlantic taking that water all the way over to Western Europe. And this